All right. Hi everybody. I apologize again for not being able to make it tonight, um, but I thought it would be important to talk about two examples that I promised you that I would do. One is for fatigue, and one is for the design of shear connectors or shear studs. All right. So before we start, let's go over what we did last time. So we talked about fatigue, and we said we have two types of fatigue. One was the load-induced fatigue, and then the distortion-induced fatigue. Um, we said we will only consider the load-induced fatigue for now. We're not going to talk about this one. And for your project, you don't have to worry about it. Only worry about the load-induced fatigue. All right, moving on. So when we talked about fatigue limit state, we said we have two limit states, or we have two load combinations. One is the fatigue 1 for infinite life, and one for fatigue 2 for finite life. Each one has its own load factor, and the equations to calculate the fatigue are a little bit different for each one of them. We say the way we decide if it's finite or infinite is based on the number of trucks or ADTT that passes through. We said if it's more than this number, for our detail 745, we consider as infinite. We'll show you an example here. This is the same example that we talked about the entire semester, and this one here we were given 800 for your project. Consider it the same, so just design for infinite life. You don't have to worry about the finite life, only infinite life. That being said, okay, this is here the first part of the sheet is just to calculate if we have infinite or finite. So given that we have only, we said we want it to be infinite, so 8 ADTT 800 is more than the limit 745, so it's infinite. The detail category, we talked about that, and we said, let's go back to this here. All right, detail category, we said for, let's see, we said for each detail there is what we call a detailed category, and has its own properties. So here, since we're only interested in fatigue at locations of cross frames, therefore we will be looking at the connection plates. That's what we're looking at. That's what we're concerned about. And for connection plate, the category is C prime, and the threshold, or the stress threshold, is 12 KSI. Again, we're only interested in investigating the fatigue around or at location of cross frames. All right, moving on. So again, this delta F, the threshold 12 from this table that I just showed you right here, it's going to be the same for you, and I can show you in it's also in the code as well. And this is the table that you look for. Moving on. Again, we have these equations for infinite life and finite life. We're using this one, delta Fn, which is the resistance, equal delta this is the applied load, equal the resistance, which is the threshold, which is 12 KSI in our case. Now, how do we do the analysis? All right, so if you remember this right here, we got this one. This is what we got from the QCOM bridge, and we got all these loads, including the 1.3T truck plus lane, 1.3T tandem plus lane, and then the fatigue truck, which has specific it has a specific let me show you here, because the axial location was specific, which has 14 feet and then 30 feet in the back. That's why we get these specific loads. And this one also includes a 0.15 dynamic allowance factor, or the impact factor. It's not the same as the other live load. So we only consider this one for calculations of fatigue 1 or fatigue 2. Alright, so we have this fatigue truck. Let's go back here. Okay, so we have the fatigue truck load, if we have negative or we have positive, and this is moment. We're talking about moment right here, not shear, but moment. Okay, distribution factor. I used distribution factor 0.43, and this is what we calculated for the interior. You could use, you will have your own load factor, and again we were doing for an interior span. If it's for exterior, we would do 0.7. Okay, if exterior, we would do 0.7, and we calculated before. Alright, so based on this, we can say the live load plus IM plus the impact, it will be the fatigue load times distribution factor. Alright, okay. Now, we can see also here that this is the range, our range of moments given. Moving on. Alright, so this table here, it kind of calculates the moment at a specific location. Alright, as we said, let's look here. Let's look right here. This is what we had as our cross frame locations. We had one here, so 20, 20, 20, 20, 10 right here. So we're talking about positive moment now. We're only investigating positive moment. Therefore, we are looking for the worst case with positive moment, worst positive moment at a cross frame location. Okay, so looking at this and looking at this guy right here, the moment diagram, I can see that the stress range for the cross frame at 40 will be the max. It's very obvious. You can check more than one, but it's very obvious that it's gonna be here. Alright, so we only have to check the cross frame at 40 feet. Therefore, we will calculate the moment at 40 feet, positive and negative, and this is what we did here. Negative, positive, all at 40 feet. DC1, DC2, and DW were also calculated. I'll explain why in just a tiny bit. So the range of moment is basically this number minus this number, and we get this number right here. Moving on. Now, loading. So now we, again, as we said, we pick the worst case at a cross frame location. We have cross frames at 20 feet in the large moment area or the positive moment area. At 40 feet, we have the largest among all the other cross frames. Alright. Okay. Stress. Where do we check the stress? As we explained before, we do the stress check at the plate, the connection plate between the girder and the cross frame. Okay, so the worst place or the worst case where we have the maximum stress on the connection plate or the weld on the connection plate would be two places. The first one is the bottom of the top flange, and the second one is the top of the bottom flange. Alright, now to calculate the stress on the bottom of the top flange, we would expect the stress to be in compression most of the time, but we want to check because we have some negative moment coming from the fatigue load, from the live load. So we want to check, is it actually always in compression or not? So what we did is the following. We said, okay, the stress coming from DC1. Let's see what's going on here. So if you look at this equation, O22 coming here, what is O22? This is O22. So it's the moment from DC1 at 40 feet times 12 to convert feet to inches times 25.26. 25.26 basically is the distance between the centroid of the girder to the bottom of the top flange, or in other words, the top of the web. Alright, divide by I. And DC1, as we said, it is applied on the non-composite section, so we use I non-composite, and this equation simply is sigma equals my over I, as simple as that. Similarly, we did the same for DC2 and DW for the long-term composite section. And this also we did the same for the live load. Now in this case here, we for the DC1, DC2 and DW, they were unfactored, no factor. We did not lose any factors, any load factors. Here we use the load factor 0.5 to maximize the effect, to get the worst case. Alright, moving on. So this one here is 1.5, and this is the load factor for fatigue 1 infinite life times O19. What is O19? The negative moment. We only consider the negative moment. Why? Because we're saying if we have any tensile stresses. We don't care about the compression. Only you want to see if we have any tensile stresses. Okay, times 12 to convert from feet to inches times 2.99. This is the distance again between the centroid of the girder to the bottom of the top flange, or simply top of the web. Alright, divided by I of the short term section now, because this is a live load. We applied on the short term section. Okay, short composite section. Okay, now if we sum all these together, we get this number, and it's negative. Okay, meaning it's always in compression. This is negative compression, this is positive as intense tension, so it's always in compression. Therefore we do not even need to check for fatigue. We're good. Alright, moving on. Now the second part, or the second location where we need to check, is the top of the bottom flange, or basically bottom of the web. Okay, and this is again at the connection plate location, or the cross frame location. Alright, how do we do this? Okay, so if we go back, we said this is our equation for infinite life, right? So delta Fn, and this is the stress range that could happen from the applied load, and this is the threshold. We said our threshold was 12 based on this detailed category. Now we need to calculate this delta Fn. Okay, delta Fn is this basically the stress. How do we calculate delta Fn? That is the following. Again, 1.5. This is for fatigue 1 infinite life, and times Q19. Let's see what is Q19 here. This is the range, so we're talking about range now. So the stress range, or the moment range, times 12 to convert from feet to inches, times 39.01. This is basically this distance from the centroid to the bottom of the web, or the top of the bottom flange. Okay, now we set our divided by I, which is just the moment differential for the short term section. Now the limit is 12. This is 7.69. We're okay. So far so good. Awesome. Now don't forget to do the check for the web fatigue requirement, which is, let me show you here. Alright, let's see what's going on. Okay, so we said we have to check for the web fatigue requirement, and it is V ultimate is lower or less than or equal to this value, and this value is basically the shear buckling resistance. And we said for fatigue we do not rely on any post buckling capacity. That's why we said okay, shear buckling resistance, and that's it. Okay, and V ultimate here is the shear in the web at the section under consideration due to unfactored permanent load plus the factored fatigue load. Pay attention to this: unfactored permanent load plus the factored fatigue load. Okay, and this is in our case fatigue 1. Alright, moving on. Now we have designed for fatigue. I hope if you have any questions, let me know. Now we'll move on to the design of the shear studs. Okay, how do we do that? Okay, so I put these in the same spreadsheet. You can do that or not do that. It's up to you. But I do it because when we design the shear studs, it mainly depends on the fatigue limit state. We do design for fatigue and strength, but the controlling one is the fatigue limit state. Let me show you how. Alright, so let's see what's going on here. So we have this table. This is the unfactored shear. So we got this basically from QCOM bridge. Again, we got the span, we got the points, we got DC1, DC2, DW. Again, shear, fatigue truck minus plus distribution factor fatigue. Yeah, and this is basically it's just the factored load. Okay, so this is the infinite life. All right, I think this is easy to get. Now, let's move on the second table. Okay, let's go to here for a little bit. So we said when we design, we have two limit states. We have the fatigue limit state and we have the strength 1 limit state. Okay, fatigue limit state. How do we design based on fatigue limit state? We find something called the fatigue resistance, and it's a value for finite life. This particularly is called ZR. For this is for a finite life, and this is for infinite life. It's as simple as that. 5.5 d squared, where d is the diameter of the stud itself, and in your case 7/8 of an inch. All right. So we have calculated ZR, and then we go ahead and calculate P. As simple as that. P depends on N, ZR, I, V's, SR, and Q. N is the assumed number of studs per row. I assumed here 3 of them. VR is basically the shear at the shear range at that location. So shear range basically is plus minus this one. So 65.18 minus 6.99 equals 65 plus 6.99, which equals this value. Okay, I assumed we have 3 per row, and in this case, and Q. Let's go back and see what is Q here. How it is it defined? Q is what's defined as the first moment of the transformed short-term area of the concrete deck about the neutral axis of the short-term composite section. Okay. In simple words, Q basically, how do you calculate Q? You multiply the area of the slab of the deck, the effective, times the thickness of the deck. That's it. I'm sorry. So the area of the deck times the distance between the slab, center of the slab, to the centroid of your the girder. Okay. So it is the area of the slab times the distance between the centroid of the slab to the centroid of the girder. That's your Q. Moving on. This is Q. It's the same for everything. I is just I for the short-term section. As simple as that. ZR. Let's go back and see. ZR we said what is 5.5 times D squared. Simple as that. P we calculate based on this equation right here. And ZRI divided by VSR Q. And we have this for P. And P is the pitch or the longitudinal spacing in this direction. Alright. Before, when you choose N, just as a hint here, when you choose N, you have to make sure that you adhere to the spacing requirement that are mentioned right here. Okay. Alright. Moving on. So we calculate P. We got all these numbers. It's a little bit different for each. We had this is the limits from 6D all the way to 24, up to 24 inches. Now, we got 8.2, 9.4, 11.12. We cannot do that. We cannot see that in the design. I mean, we can, but we should not. Okay. So we will use just integer numbers. For example, we'd use, let's say, 8 inches, 9 inches, 11 inches. Also, we do want to use a lot of numbers because it's very hard as far as construction. So what we do, if we have a short span, let's say 50-60 feet, we'll just use one spacing. For example, in this case, 8 inches, for example. If we have like 100, 200, we'll do maybe 2 spacings. We start with 8 and then maybe also 10. If we have more, we can do more. Alright? Just don't make like 5 or 6 spacings. That's too hard to construct and makes a lot of confusion. So now we calculated the shear stud spacing based on the fatigue. So now we know what is the spacing, how many do we need. Alright, now going back, we said we have fatigue limit state and we have strength 1 limit state. Based on strength of limit state, we have to do the same thing. Now, it is important to note that the fatigue limit state almost always controls. But we still have to do our due diligence and check for strength limit state. Okay, how do we do that? Let's go back to the theory a little bit and then we'll come back. Alright, let's see. Strength limit state. So strength limit state, we have basically two parts. Okay, we have the resistance part and we have the applied load part. The resistance part is controlled by two things. The first one is the strength of the concrete or the strength of the stud. So if you look at this equation, Qn equals 0.5 ASC the square root of FC prime EC. So ASC is the cross-sectional area of the shear stud connector. So basically this is the strength of the concrete. Okay, less than of or equal to ASC F ultimate. So this is the strength of the shear stud, how much load it can take. Alright, so we calculate both. Let's go back to here. We say Qn for concrete 0.5 times the area times square root of this equation. Okay, we got some number. Same thing for stud, and our case if ultimate was 65, and this is what I think is the same as you have. Okay, now QR is just simply Qn times phi SC, which is 0.85 in this case. Alright, go back here, just 0.85 times the minimum of these. Alright, moving on. Now VH is basically the load that we apply, as simple as that. Alright, so VH can be calculated also in two ways. We have two cases to calculate VH. The first case, case A, is when we have the centroid, or I'm sorry, the PNA in the deck. In that case, all the maximum modes that could be resisted by the studs is all of this, which is FYAS tension. Okay, because we're transferring forces from the girder to the deck. So the maximum force that could happen is the maximum force in the girder because of the PNA here. Case B, on the other hand, if we have PNA here, is the other way around. It's all the force that is in the concrete deck, which is this one. Okay, now to make things easier, to worry about it, just calculate case A and case B without worrying about the PNA and pick the smallest one. Alright, let's go back here. So that's what we did. Case A, case B, we get some numbers. It's a little bit different in the middle because we have different section of different girder section. So we calculated case A and case B and we got the smallest one. Okay, NS, let's go back here. Now NS basically is the number of shear connectors needed to cover from the maximum shear, from the support to the maximum moment. Support to maximum moment. Alright, and equal VH equal divided by QR. Again, so demand divided by resistance or capacity. Alright, so if we look here, NS, let's see, so it's the minimum, and we round everything up, so it makes sense, the number as number of studs, number of these divided by this. That's what we got. Now Pmax, which is basically the shear, which is the pitch, which is the maximum longitudinal spacing of the studs themselves. And I calculated this based, it's basically the following. So we assume that the maximum moment happens at 0.375 of the length of the span, and this makes sense because if you go here, let's see, this is here, this is the maximum, around 36 feet, out of 90 is about the same. Alright, okay, so times 90 times 12 to convert from feet to inches, times 3 is basically the number of studs per row divided by NS, and you get Pmax. Alright, you can notice here that Pmax here is a lot larger than this one, so the fatigue one controls, but we have to do the check anyway. Alright, So I'm done with the shear stud spacing. I think that's it for this video. I'm gonna conclude now. Please send me your email with any questions that you may have, and I will make sure to answer as quick as I can. Thank you so much, and have a good night. Bye.